Welcome to all of you. In this lecture, we are going to discuss about the design of 3-bit asynchronous mod up counter as well as the 3-bit asynchronous mod down counter. So let us start with the design of the mod up counter. The first problem we are going to have with this is design a mod 5 up counter using IC 7476. So we are going to have a design of mod 5 up counter. Let us first understand what is this mod 5 up counter. So up counter, we know that it starts from the initial value 000 and it will continue towards the maximum value. Now the mod 5 indicates that so from this counter it has to count only the first 5 values, after which it must come back to its initial value. So with respect to the up counter, the first 5 value stands with 000, 001, then 010, 011, 100. So these are the first 5 values. After that, automatically it must come back to the value 000, which is the initial value. So in order to perform this from the functional table, we are going to make use of two concepts. So first one is the criteria of preset is equal to 0 and preset is equal to 1 and clear is equal to 0. This is what one criteria we are going to make use of. The second one is for the regular count operation, we are going to keep the flip-flops in the toggle mode. Now this is what the complete circuit with respect to the mod 5 up counter. So in the regular up counter, what we do is we are going to connect the clear to the VCC so that we can have count from minimum value towards the maximum value, and then automatically it will come back to the minimum value. So in this case, we are not going to do that. We are going to design a mod 5 up counter. So that means the count will be terminated somewhere in the middle and it will come back to its initial value. Therefore, we are going to have a separate arrangement. So for the clear signal, we are going to give it as output of the NAND gate. And to the NAND gate, we are going to connect Q0 as well as Q2 as input. And remaining all other circuit remains as a regular up counter design. Now let us have a clear understanding of why we are going to connect only the NAND gate, why not any other gates further. So let's have a clear understanding of it. Now we are going to have a design of mod 5 up counter. So in a mod 5 up counter, it is going to count from 000 up to 100. Then after it must reset and all count values must come back to the value 000. So we need to perform a clear operation after this particular stage. Therefore, the output of the NAND gate will be connected to the clear signal. So two points we need to remember at this instant. So we are working with the active low signal of the clear. That means clear is a active low signal. Active low in the sense, if we give a 0 value to the clear, then the output will be reset to 0. So we are working with the active low signal. So whenever we are working with the active low signal, it is always required to make use of only the NAND gate as the logical gate operations. We need to make use of the NAND gate provided if we are working with the active low signal. So this is the first condition. The second condition is, so we are working with the up counter design, mod up counter design. Whenever we are working with the up counter design, so to the location up to the point what we want to make the counting operation, after that whatever the count value is there, from that we need to tap the ones. Ones in the sense the Q0 is 1 as well as Q2 is 1. These two signals we need to tap and they will become input to this NAND gate. So this is the second condition. If we understand these two conditions or the criteria very clearly, we can make mod design for any of the counters. Therefore, in this particular case also, Q0 and Q2 are getting as input to this NAND gate. Now let us make a clear understanding how this NAND gate is going to work like. Now from 000 till 100 there will be a normal counting operation with respect to the clock input. Then after, when the clock is applied, as a continuation of normal count operation, the count value will proceed to the value 101. So this 101, the Q2 and Q0 is given as input to the NAND gate, and for the NAND gate, if I give the input 1 and 1 over here, then output of the NAND gate will become equal to 0. And that output will be given to the clear signal. So that means clear will become equal to 0. Now as per the functional table, if we observe, so clear is equal to 0 in the sense we are going to get the output as 0. Therefore, we are not able to observe this as the output in the trainer gate. Immediately it will shift to 0, 0, 0 in an asynchronous manner. So that means whenever clear is equal to 0, clock J and K or don't care, output will be directly driven to the value 0. That is the clear state. Therefore, immediately all the flip-flops will be driven to the state of output 0. So we get the value 0, 0, 0 at any instant of time when we get completed with the count operation. So let us have a step-by-step understanding of what happens at each of these states. And also you must make an observation that, so when we have connected Q0 and Q2, that means only the bits which are having the value 1 we have tapped, then there must be same condition somewhere previous. That can be a consideration. But if we make an observation throughout, Q0 and Q2 are not simultaneously 1 before this particular point. You can make an observation of it. So here it is 1 and 0. Here it is 0 and 1. So here 0, 0, 0, 1, 0, 0. So these two bits will be simultaneously having the value 1 only at this particular instant, not anywhere before this. Therefore, we must consider only the bits having the value 1 while making this circuit. So let's have a better and more understanding in a step-by-step manner. Okay, so we are going to have the first step. So configuration is as shown previously itself. The NAND gate is connected to the clear, right? And all other circuit remains the same as a regular up counter part, right? So let us start with the beginning value, that is 0, 0, 0. So inputs are kept in the toggle state. Therefore, J and K inputs for all the flip-flop remains 1, 1 at all time. And output we are going to have the all zeros, 0, 0 and 0 we are going to have. And at this instant, what is the output of the NAND gate? Because output of the NAND gate is connected to the clear of each JK flip-flop. So Q0 and Q2, both of them are equal to 0. Therefore, 0, 0 is the input to the NAND gate. Output will become 1. Therefore, so it is connected to clear. So clear has no effect on the count. We can continue with the regular up counting operation. Now at this instant, when the clock pulse is applied, the count will get moved to the next value. So count has moved to the next value 0, 0, 1. So here it is 0, 0 and 1. So toggling operation, therefore output has got changed. So now here 0, 0, 1 we are having. Again the value has been changed. Make what is the input to the NAND gate and what is its output. Now Q0 is 1, Q2 is 0. So 1 and 0 are the input to the NAND gate. And again from the truth table, output still remains as 1 only. and that is given to clear, so no problem to continue with the up count operation, right? So whenever the clock pulse is applied, it will move to the next value. So here is the next value 0 1 0, right? So 0 1 0. So input to the NAND gate is 0 0 and output remains as 1. So no problem, we can still continue with the counting operation. Again we are going to apply the clock pulse so that the count can move to its next value. Now the next value is 0 1 1. So 0 1 1. Now the input to the NAND gate is again going to be the 1 as well as 0. Output will remain as 1 as per the truth table of the NAND gate. So again the continuation of the counting is still there. So apply the clock pulse. We are going to get the next value 1 0 0. So input to the NAND gate is going to be again 0 and 1. So output still remains 1. Right? Now here and onwards is what the most important fact we are going to have. Now after this again we are going to apply the clock pulse, and as a part of regular counting operation, it will simply take upon the next count value, that is 101. Now what happens, that is the most important fact which we have to understand. Now Q0 is equal to 0, Q0 is equal to 1 and Q2 is equal to 1. So here it is Q2 and here it is Q0, and that will be given to the input of NAND gate. So input is now 1 and 1, and as per the truth table of the NAND gate, output will automatically become equal to 0, and this 0 will be given to the clear signal, right? Now as per the functional table we can observe that, so preset is still equal to 1, that is connected to VCC. We are not going to touch that one. Now clear has become equal to 0. So preset is 1, clear is equal to 0, means what? Clock JK or don't care, and output will be set equal to 0. Therefore what happens? So when output of NAND gate is equal to 0 and it is being given to the clear signal, output will be automatically driven to value 0. And this is what we are going to have. The output of each flip-flop has been driven to 0, and it is going to happen in an asynchronous manner. So therefore what happens, even though we are going to have the value 101, it is not possible for us to observe on the trainer kit instantaneously. That means in the asynchronous manner, this value will kept changing to value 000. So that's an instantaneous happening. Therefore it makes a sense for us that we are directly jumping from 100 directly to the 000, but there will be one intermediary value 101 which is not observable for us, right? So this is the fact that we have to consider while making the design of it. So whichever the after 5 values, whichever the next value is there, considering that particular value, we are going to have a design and the logical gate selection. Now for better understanding, let us have a circuit representation for one more mod up counter. So here I am going to consider the mod 4 up counter design. So this is what the design we are going to have. Again, NAND gate only I am going to make use of. There will be no change with respect to that one. So first let us understand what is this mod 4 up counter. From the beginning value, that is from 000, it has to count total 4 values, after which it must reset back to the 0. So this is the first value 000, then 001, 010, 011. So 4 values are completed. For the next value, this next value must not appear, it must go back to 0 directly. Therefore, while designing, we must consider the next value, that is 100 we have to consider. So in this particular sequence, which bit is having 1? So only Q2 is the one bit that is having 1. No other bits are having 1. Therefore, for all design purpose, I'm going to consider only Q2 and output, and the Q2 will be given to the NAND gate. Therefore, so here we can observe, so we are having a minimum of only 2 input NAND gate. Therefore, so the Q2 is being shorted to the both the inputs of the NAND gate, and output of the NAND gate is being given to the clear. So this is how it is going to work. Any of the explanation for this I'm not going to provide step by step. I hope from the previous explanation you have understood how it is going to work step by step, and you can have design of any such mod up counters. So criteria you must remember. So we must record to NAND gate because we are working with the active low signal over here, and with respect to the truth table, in case of up counter, remember in case of up counter, so whichever the bits having the value 1, only those signals we need to tap, and that is dependent on again only those ones we have to tap, and where we have to tap, that is depending on the mod counter. Mod 4 it's a different tapping, only Q2 will be tapped. Mod 5 in that case Q0 and Q2 are being tapped. Those bits which are having 1 we have just tapped and given as input to the NAND gate, right? Okay, so let us proceed with the design of the down counter. So here we are going to have only one design, so that is a design of mod 5 down counter. So let us first understand what is this mod 5 down counter design. So down counter is nothing but we are going to start from the highest value and move towards the minimum value. Highest value towards the minimum value. Within that, mod 5 counter in the sense, so highest 5 values will be counted and its next value must not be visible for us, and it must move back to the highest value once again, right? So that means highest value we must reset it back. For that purpose, with respect to the functional table, what we need to make use of, we need to consider the preset signal, right? Preset signal is always going to set the output to 1, and that is what we require when we are working with the down counter, especially mod down counter. So clear has nothing to do over here. So clear will be always kept equal to 1. That means it will be connected to the VCC. And then preset, wherever according to the requirement and the design, we are going to make preset is equal to 0 at that particular instant, and then automatically the output will move to the highest value, that is equal to 1. So this is one what we require. Second one is, so preset is equal to 1, clear is equal to 1. So and toggle condition. So that is we need to perform regular down count operation. For that, so we need to have this one. So this combination as well as this combination from the functional table we are going to adopt to design a mod 5 down counter here. Again remember, mod 5 in the sense from the highest value, when the count is moving towards the lowest, we need to count first 5 values. So this is 1, 2, 3, 4, 5. After that, I must not get anything else. It must simply come back to the highest value, that is 1, 1, 1. Right? So let's have a better understanding of it. Now this is what the complete realization of the circuit we are going to have. So here you can observe that with respect to mod 5 counter, the signals Q0 and Q2 are tapped, and that will be given to the OR gate. Remember, we are working with a down counter, so here we are going to make use of the OR gate, and output of the OR gate is being given to preset of each of these flip-flops. Right? Let's go further with this. So why OR gate? Again, that's a question. Why OR gate? Why not anything else? Just like a NAND gate, what we discussed previously. So OR gate. So in down count operation, we are going to tap the zeros. Remember, in the down count operation, we are going to tap the zeros. So, and OR gate is the only case which we can consider when both inputs are equal to 0, the output will also be 0. That criteria is being satisfied by the OR gate. Therefore, we are going to consider this OR gate. And why we need the output as 0 at that particular instant? Preset is active low. So we need to send a 0 signal to the preset. It's an active low. Therefore, we are expecting when the input is 0, 0, output must also be equal to 0. That criteria has to be satisfied. Therefore, we are adopting the OR gate. Remember, preset is active low. That's why we are adopting OR gate with respect to the input values. Right, coming to the understanding of the design. So it is a sequential decrement we are having, started with the highest value 1 1 1 and then we move towards the 0 1 1. So 5 values are completed, and by default we are going to get the next decremented value, that is 0 1 0. And as I told you, we need to tap only zeros. Which bits are having zeros? Q0 is 0, Q2 is 0. Only those two bits are taken, and that will be connected as a input to the OR gate, right? And corresponding output of the OR gate is connected to the preset of each of the flip-flop, right? So when it is connected, when both of these two become 0, output of the OR gate becomes 0. Therefore, preset input will become 0, and we will be satisfying this particular criteria. Therefore, output will be automatically set to the highest value, right? And you must also verify that. So in any of the previous values, the Q0 and Q2 are not simultaneously 0. That you can verify. So here it is 1 and 1, 1 and 0, 1 and 1, 1 and 0, 0 and 1, and only in this particular case it is both of these two bits are 0. That's why it is going to work out. In all other cases, output of this OR gate remains as 1, which is not going to affect the regular down count operation, whereas in this particular case, these two bits become equal to 0, which will input preset is equal to 0, which makes the output set back to the value 1, and again we are going to get 1, 1 and 1, right? So let's have a step-by-step understanding of it. Okay, so here we are going to have the circuit realization. So we are going to have the inputs JK always equal to 1. So we are keeping them in a toggle condition, and remember we have nothing to do with the clear over here. Therefore clear is connected to VCC, right? And then the preset signal. So output of the OR gate is connected to the preset of each of the flip-flops. That our connection is being done over here. Then we are going to consider that we are at the highest value, that is 1 1 1. So output is being represented as 1 1 and 1. And remember, the clock to the subsequent stages will be from the Q bar, that is being represented over here. And you can also make an observation how Q changes, how Q bar changes. That's why the next stage is going to have a variation in the output, right? So let us go step by step. We are at the highest value. Now the clock pulse we are going to apply, then it is going to shift to the next value. So here is the next value we have got, so that we can observe over here. So it is 1 1 and 0, 1 1 and 0 we are going to have. Correspondingly, you have to make observation of the Q bar at each stage, and then at this stage we are going to apply the clock pulse. It will move to its next value. So it is 101. So 101, we are in the regular down count operation. Again apply the clock pulse. We get 100. So we got 100, and then apply the clock pulse again. So we are going to get 011. We have got 011. So with respect to our mod 5 down counter, 5 values are completed, right? In all these cases, you must observe that output of the OR gate is remaining as 1. That you must observe very carefully. At each stage, the output of OR gate is remaining 1. So that means preset is equal to 1. We are in the regular down count operation. That is preset is equal to 1, clear is equal to 1, JK in the toggle condition. That's what the criteria. So we are in the regular down count operation. The next step is what is more important for us, because there it is going to have a preset operation. Now after this, when we apply the clock pulse, This is what we are going to get. As a part of regular down count operation, we are going to have 0, 1, 0. Right? Now Q0 and Q2 are connected to the OR gate inputs. Therefore, Q0, Q2 now equal to 0 and 0. So input to the OR gate is 0 and 0. Therefore, by default, output of the OR gate will become equal to 0. Now preset will be given with the value 0 of each flip-flop. Therefore, we are at this stage now. Preset is 0, clear is 1. So then what happens? From the functional table, output will be set equal to 1. That means Q of each flip-flop will get the value 1 asynchronously. Therefore, what is going to happen? So we are going to get this value 1, 1, 1. So each of the flip-flop has got preset. Remember, it is not a reset, it is preset, and the output is now equal to each flip-flop 1, 1 and 1. So now we have got the initial value of the down counter, that is the highest value. Again, if you apply the clock pulse, the cycle will keep repeating. Right? I hope we can have a design of any such down counter for any other mod values. So thanks for joining.